Right, so thanks for having me. Still a bit jet-lagged. I got in to the guest house at 2:30 this morning, and still a bit on the German clock, of course. Right, so I'm going to talk about neuromorphic computing at cloud level, centered a little bit around our hardware, Spinnaker 2, but also general types of algorithms in that direction. And actually, it's a huge change of scenery for me, right? This was a week ago in Norway. So I was skiing with my family for 2 weeks, and really we had snow like crazy. Actually, road conditions were a lot worse usually than this picture, because there was fresh snow and ice on the tracks. So I really also saw upturned vehicles on the side leaning against that snowball, right? That had a crash. And minus 20 degrees. So you basically had 3 layers of gloves on. It was still getting cold. So here I'm just sweating. Anyways. Right, so a little bit about my group. So I had a group of mostly chip designers at TU Dresden, but also algorithm people, right? Because you need to do hardware software co-design, right? Because the standard software stacks, machine learning, whatever, they don't work out of the box for us, right? That's been, of course, one major thing that's hindering neuromorphic adoption. You need common software stacks. So I've got algorithm people. We have a line of neural implants, so even have medical people, biotechnologists on my role. And of course, yeah, we all get excited about chips, but usually people get excited about something moving. So we also do quite a bit with robotics, for example, so really putting our chips somewhere where they do something. We've got what I call our biotope spin-offs. So we've got 4 spin-offs currently off the chair. That's RASIC, Silicon Alley, Coinbauer, Spin Cloud Systems, and a new one on the implant. It's just in foundation. So that's about 250 people, and why I call it a biotope is basically because those are all still very closely connected to the chair. And when I do something like Spinnaker 2, like this big system, I basically farm out work. So there's the guys from Silicon Alley, they help with the link design. Guys from RASIC help with the low power circuit design using this 22FDX technology of Global Foundries optimally. So I've got access to a huge kind of library of IP components of circuit building blocks that I can use. Right, so what do? We mostly focus on system on chip design and of course the systems that are built on top of these chips. So, which means we don't focus like your usual circuit chair at any one of those particulars, like just the network on chip, just the ADCs, sensor interfacing, whatnot. We do all of those. We even do standard cell design, whatnot. But we very much kind of subsume it here, right? So we don't usually, for example, get the last 10% or whatever out of this here to get a nice ISSC publication, because if I then put it into the overall system on chip, the whole system wouldn't work, right? So we basically design very much top down. We do this quite often. So we usually have 3 to 5 tape-outs per year. Even before Spinnaker, we built a lot of systems that basically were used by other groups. So you usually don't need one of my PhDs kind of fine-tuning the biases on one of our circuits. Basically, they work out of the box. That's why other people use them. And we do this, especially with Spinnaker, across many orders of magnitude, right? So on Spinnaker, there is single transistors we touched, for example, in all the power delivery network. But of course, the whole machine is 10 to the 14 transistors. So it's like 14 orders of magnitude that we do design in. Right, and of course we're part of Silicon Saxony, right, which is the 5th largest ICT location in the world, which also means it's the largest in Europe. 36% of European chips are produced there, and that's even before TSMC is now setting up the new fab. Hands up who gets that reference? Okay, at least a couple of them. Right, so yeah, that's Monty Python, and no one expects the Spanish Inquisition, right? They always pop in that clip. Right, so I'm going to talk about my take on bio-inspired computing a bit, then on Spinnaker 2, and then on a lot on the algorithms. I'm going to bombard you with 5 different types of algorithms that I think exemplify where we should be going at the very large level in going for adopting brain-inspired principles. So right, we already have superhuman performance in a lot of AI, right? So ChatGPT, whatever, they can do college level entrance exams, even kind of bar exams and legal stuff. They actually have recently gotten very good at mathematics stuff as well. So why should we even look at biology, right? The brain is an old thing. But energy efficiency, of course, is a big thing, right? So in-memory computing, near-memory computing, less resolution, right? Especially for training, you still need double precision floating point. We need to get away from that. Then, of course, static sparsity, but also a lot dynamic sparsity, which is recently catching on in machine learning. So that you basically do on-demand computing. You don't need to activate the entire network to answer, for example, a prompt in GPT. I'll give you an example of that later on, right? So that's actually the biggest contribution in my mind to close this 10 to the 7, 10 to the 8 energy gap we still have between the GPU data centers and the brain is basically this on-demand distributed computing, right? Then, of course, not just AI, right? In general computing principles, the brain is doing something that an ordinary high-performance computing is just not able to do so far. Ordinary HPC maxes out at like 200-300K cores, right? Normal supercomputing. You just usually can't break down an algorithm to take advantage of more cores. And the brain, of course, is using whatever, 80 billion neurons in parallel. So, yeah. And brain has figured out how to do that by mostly being asynchronous, right? You don't need a lot of handshaking, which also means you don't run into Amdahl's limit. You basically don't need to wait for processes on each other. So that's also interesting from supercomputing perspective. Then, of course, learning is a lot different in the brain, right? So we can adopt that because training is the reason why we have now these, in XAI, these 100,000 GPU big clusters, right? Because training in inference is getting more and more efficient. So people are streamlining their chips for whatever transformer networks. But learning isn't catching up so far. So that's definitely something biology can still give us. And of course, merging different AI streams, right? I mean, what a CNN does, convolutional network, that's like what the lower layers in visual cortex do. But even though if you go up to MT cortex, let alone associative cortex, you have mostly more like something like symbolic AI, right? You also have a lot of probabilistic computing in the brain. So that's also different aspects, what DARPA calls the third wave of AI, merging those different streams with a bioinspiration. That could also be something. Whoop. Let me get this started. So that's just, whoop. To animation, right? There's spikes running around between a couple of neurons. You got the synapses here. And of course, yeah, according to the strength of the synapse, the pulse then gets somehow multiplied, gets integrated at the soma. Right, so it's a deceptively simple substrate. Okay, neuroscientists are going to kill me, right? Because there's a lot of complexity already at the neuron level. So good, you're not hearing this right now. But from a computational perspective, right, if you simplify this to leaky integrated fire neurons, then it's very simple, right? So the complexity, to my mind, comes at scale. If you go up to those 10 to the 11 neurons and 10 to the 15 synapses. So we really need to look at biology also from this. Neuromorphic is always this bottom-up thing, right? Let's just cram leaky integrated fire neurons together and see what happens, in a sense. Okay, I'm going to get burned at the stake at some point today, but don't worry. But machine learning is more about top-down, right? They go from a solution and then they design the whole architecture behind it. So that's how I also want to look at the brain a lot more, right? So you've got multiple layers of self-organization in the brain, right? Yeah. Brain is a lot about gating information, right? So that's what these spikes are all about. Brain, as I said, is asynchronous. It's highly parallel. And it's actually very slow at the individual neuron level, but of course it's very fast because it parallelizes so much at the system level, right? And of course, computation and memory are co-located as much as possible. Right, so if we look at the eye, just to give you a simple example, right? Those 4 or 5 layers of cells in the eye, they already make this kind of second order derivative, this Laplacian of Gaussian. So basically everything that's a constant value in the image, everything that's a constant gradient in the image gets set to 0, so you only get the edges left over. Again, that's a simplification. But the interesting thing is already with that very simple principle, you get 100-to-1 abstraction, right? 100-to-1 compression. And then you encode that, of course, sparsely on the ganglion nerve. So typical sparsity in sensory areas about 10 to the minus 2 to 10 to the minus 3, memory areas 10 to the minus 4, associative cortex 10 to the minus 5. So the brain is very silent. The brain is very good at kind of providing structural resources, but having them in a deep power down mode and only activating them when really needed. So really gating stuff and only activating it when you needed to, whatever, solve some certain task. Right, so the high level, this is the stuff I'm focusing on, right? Hierarchical distributed computing, which also means, of course, near memory computing if you distribute it. As much temporal sparsity as I can get at multiple levels, right? This could be, if I go to machine learning, the single ReLU level, that you just change the activation function of a rate neuron, that you basically get more zeros activation, but it could also work at an attention level, it could work at a network level, network gating. That's all the ways how you go temporally sparse. Then, of course, recasting. So I'm coming mostly in this sense, right? I also have a computational neuroscientist, half of my brain. But these, what I'm going to tell you in this talk is mostly coming from a machine learning perspective, right? So how to change machine learning into something that takes these principles into account. So asynchronity, right? That's also a big thing. Most machine learning algorithms these days are still synchronous. So how to recast them. Then actually, at a high network level, I also believe a lot in dynamic computation, right? What the brain does. The brain is not as static as a machine learning network. So it really is about integrating information as it comes in, reaching some decision, passing something on. So it doesn't necessarily have to be at the single leaky integrated fire neuron level, but definitely, for example, if you have an RNN network at the network level. And of course, very much like kind of that the brain respects physical constraints. So that's something also a lot of supercomputing algorithms don't really do, right? So supercomputing algorithms usually assume all-to-all connectivity, whatever. They don't care about the physical structure of the brain, about the physical structure of the compute machine, right? So designing an algorithm that actually, for example, has some physical notion of where it lands on a machine, that you have bandwidth limits, that basically stuff that's like locally, you can have more dense connections, and if you go globally, you need to be kind of dying out with distance, right? This is also something we can learn from biology. And that's not necessarily just AI-centric. This is really also for supercomputing, that you recast algorithms in a way that you get these kind of, between the different parts of the algorithm running on different processing elements, you get this kind of connectivity matrix. Right. Again, I'm trying to get this into the network at a top-down level, as I'm going to show you in the algorithm examples. The reason I'm not so much going for the leaky integrated fire neuron level is mostly because at the moment we probably don't even need it, just to get a first kind of get the first 1 or 2 orders of magnitude improvement in machine learning. You don't need to get to leaky integrated fire. And the other thing is that, to my mind, I mean, the brain does all these dynamics also at the single neuron level, probably for a reason, right? The brain isn't stupid. But we don't have training that can actually take care of that, right? The best we can do with the leaky integrated fire network at the moment is still train it in a rate-based way and just get the weights across basically and retrain a little bit, right? We treat it almost like a rate-based network. So that's why I'm not that much, probably at some point we're going to arrive at the leaky integrated fire neuron and probably even more complex stuff like synaptic dynamics and whatnot. But we need to actually figure out the training algorithms, because this is a huge training space, right? Compared to ordinary machine learning, where the single neuron is very simple, this space opens up so many dimensions. It's kind of comparable to what the difference between feed-forward and recurrent networks. I mean, machine learning has been mostly feed-forward networks for like 10 years. They've always outdone the recurrent networks, GRUs, LSTMs, except for certain cases and time series. And despite the fact that RNNs are theoretically computationally more powerful, especially for time series. But now, for example, the big thing is state space models, right? State space models, they are starting to outdo a lot of what the feed-forward models are doing these days, and they do it at less parameters, at less computation. And the one thing that's different now is someone has figured out how to train recurrent networks in the form of state space models efficiently, right? We now have a training algorithms that can actually take care of this huge complexity that opens up if we introduce recurrency. So that's where I'm coming from. We probably need something similar, some training algorithm revolution to actually go all the way down to these very bio-inspired networks. Right, this is just a little bit of shock and awe. So yes, we get noticed for what we do. So we got, for example, €1 million BMWF award for Edge AI. The German version of DARPA, Sprint D, has awarded us the first and second round of the new compute challenge in Spin Cloud Systems. So the company we formed around Spinnaker 2, we got an ERC transition grant that's very prestigious. And actually what I'm most, what I find most interesting is if you think circuit design, right, the top conference is ISICC. We're actually these days more prominent on those top machine learning conferences than on circuit conferences, right? So people are really starting to notice this kind of merger of bioinspiration and machine learning that we do. And yeah, we've got hardware, of course, same as the Intel guys, same as Loihi, sitting around in Sandia and Oak Ridge. Right, so let's briefly talk about Spinnaker 2. Okay, who hasn't heard about Spinnaker 1? Then we can make this short. Okay, right, so let's do a short intro. Anyways, Spinnaker comes out of Manchester. That's Steve Ferber's group. Steve Ferber was one of the two original architects of the ARM system architecture. So basically, yeah, ARM processors shipped in billions these days per year. So quite famous there. And he went back to university and said, okay, what can I do with something like 1 million mobile phone or processors, very small processors in a supercomputer, right? That's what you usually do in a supercomputer because you need these big processors, you need big, large packets, synchronization network, very complex interconnects in your ordinary supercomputer because you need to solve all this time interlocking, get message passing going and whatnot. And that's all what you not, I mean, ARM processors these days have gotten more powerful, but back then it was really microcontrollers. So what can you do with 1 million microcontrollers hooked up in this toroid structure? And he came up with brain simulation because, yeah, very simple. You run the neurons and synapses as code in the individual nodes here, and you have a very lightweight communication network, spike-based. It basically just passes unidirectional messages. So you don't get handshaking, you don't get time interlocks. You have a global time scale running across the entire system. So time models itself as the usual neuromorphic paradigm. So this is a real-time system that's also different to ordinary supercomputing. Supercomputing always slows down when the system gets faster. This thing is designed, in the case of Spinnaker 1, up to 1 million cores, in the case of Spinnaker 2, up to 10 million cores, to stick with a millisecond. So really, everything, the whole communication across this machine, the whole input, the whole output, the whole computation happens inside the millisecond. So this is really kind of a quality of service, what you have in the machine that's not usual in supercomputing. So, which basically means you can let the individual nodes just run totally by themselves. And when they emit a spike, have reached some decision that needs to be communicated in whatever way, they just shoot it off to the receiving node, and they can basically assume that it lands at the receiving node, gets computed at the receiving node, inside the same time scale. So that's how you keep, I mean, in supercomputing you do all the handshaking to keep a problem coherent. Here you just have this global time scale to keep the problem, whatever you're computing on the machine, coherent. Right. And then in the beginning of the Human Brain Project, Steve and I met up and we said, okay, let's do Spinnaker 2 together, because we had been doing multi-process system on chip design for a while. But Steve is more this architecture guy, so he does this top-down thing, more from the computer architecture. We were more the bottom-up guys. So we had developed all these individual building blocks, process building blocks, bus building blocks, power management, whatnot. So that kind of fit together very well. So we put in all we knew, dynamic voltage frequency scaling. So basically each individual processing element, so the ARM core, but also all these numerical accelerators, adjusts itself to the incoming workload. So that's kind of what you usually want in neuromorphic computing, right? If you don't have spikes coming in, usually you shouldn't draw power. So that's this kind of thing that we're approximating by going to different voltages, going to different clock speeds, or even going completely into power shutoff. Yeah, of course, a lot of near memory computing, memory sharing, etc. Then we put in also machine learning accelerators, some multiply accumulate arrays. We put in what we term neuromorphic accelerators, so X block functions, true random, pseudo-random number generators, so true random that actually work off thermal noise of clock generators, which we anyways have. So we get those at virtually no overhead, because anyways the clock needs to be individually adjusted per core. Of course, lot of network on chip stuff. So this is actually almost like an AER network, but serially. So it's a high-speed interconnect network between the cores, between the chips, but it's able to power up and down inside a nanosecond. So not like your usual supercomputing link, which needs to be up and running the entire time just to stay balanced in the DC level, but actually basically you have a sparse packet, needs to be transmitted, link goes up, transmits it, link powers down again. So we try to be energy proportional in the communication, we try to be energy proportional in the computation here. And then there's adaptive body biasing, so that comes from our spin-off company RASIX. That's a unique feature to this FD-SOI technology. So we have the silicon on insulator, we got basically a backgate going into the transistor, which essentially lets us narrow down the manufacturing, aging, and temperature spread of the threshold voltage that you see from the gate of the transistor. So basically this huge sigma curve where you need to basically put the VDD, the supply voltage of the transistors, very much outside the sigma, that you know that they still basically all perform timing clean. You can actually narrow this down, and that way you can get the supply voltage down to 0.45 volts. So that's a huge thing, because usual FinFET technologies, they still run at 0.7, 0.8 volts, and power scales at least square with the supply voltage here. So we basically get between a factor 2 and 4 advantage on FinFET technologies just by being able to reduce the voltage here. Right, so that's the machine. That's actually, still a bit currently under construction. So we've got the first 2 racks here filled. The rest are just now getting delivered the boards. So physically, it's, as I said, 10 million processors spread across 70,000 chips, across 16 racks. It is still the largest real-time AI platform worldwide, so real-time this millisecond with 10 to the 14 parameters. It can do all these kind of hybrid things. Yes, and of course, on selected benchmarks, outperforms, especially those real-time benchmarks, the regular GPU crowd. As I said, it has this basically adaptive feature ramping up and down according to the activity coming in. So that's kind of the way I see Spinnaker, right? You get this AI DNN almost like a mini GPU. You get flexibility like a CPU. So you still have these ARM cores in there, able to run just about any code. And you get this probabilistic computing. So we also do a lot of quantum computing emulation, or even kind of what the D-Wave machines do. So QUBO type stuff. So optimization, so heuristics, Monte Carlo sampling on the machine. So you get this brain-like efficiency, you get this real-time stuff, and that on average gives you about a factor 10 to 100 speed and energy advantage compared to either the GPU or the CPU crowd. Just because we're hybrid, right? So if you have a GPU machine and you do a drug discovery problem, just about 1/3 of the compute load of your usual drug discovery problem. Yes?
How you're doing the routing here.
The routing?
Yeah, because you want to address individual neurons, right? So the bus would change because the more number of processors you add, the number of neurons would change and your bus width would change, isn't it? Or?
Not really. It's the same as in Spinnaker 1. So it's a hierarchical multicast architecture. So at every node, so it's really point-to-point connections. And you just know the way. So if you have a source ID that's going with the packet, and according to the source ID, each node knows where to send it to the next node until it's really at the. So each node only decodes the path to the next node until you're in the target node, and then you go into the individual neurons. So what you're writing is basically the routing table in the individual nodes, and that basically gets decoded by the source address of the neurons. So if you yes, in essence, yeah, but this machine is geared for like 20 billion neurons at 10,000 synapses each. So it's pretty well designed. So I don't see a lot of use cases where you're actually going to exceed those routing tables. Okay, so that's very short toy example just to get you started. That's a DVS camera. I already heard that Kalel is already hooking up the SCAM sensor also to Spinnaker, so we got a couple of boards along, of course. And this is mapped kind of, this 128 by 128 input space is mapped to 4 cores on Spinnaker. And as you can see, there's like 2 levels of power savings here. So one is just the sparsity coming from the sensor. So the core adjusts its power level and its operating frequency. No, that's the input events. Sorry, and the power level according to the spikes coming in, right? So it really doesn't need like a GPU. It doesn't need to run all out just to be able to catch the theoretical maximum of the stuff coming in from the sensor. But it actually, let me restart it. It actually scales energy with the amount it really needs to compute. The other thing is we've got a very simple hand tracking running on here. That's the red dot. And this is like an attentional mechanism, right? So only the core gets activated where the red dot is. The other ones are in power shut-off. So you can see basically the other ones are completely in sleep mode and only, and see, there it crosses over. So that's like 2 levels. Each of them saves about a factor 3 to 4 in power compared to GPU solution if you put this on a Jetson, for example. So in sum, you get in excess of power savings factor 10, 15, I think, compared to a GPU solution, right? So that's a very toy example, kind of 2 layers of dynamic sparsity here. Yes?
Where are you running this attention mechanism model?
It's not really an...
Is it running on one of the cores?
Actually, this one was in one of the early Spinnaker prototypes. So I think, Khalil, I think we never ported that to the real Spinnaker, but it's a trivial task, right? But it's the attention mechanism is really just where is the center of gravity for the hand, and if the center of gravity moves to the adjacent quadrant, we need a little bit ahead notice basically, so we compute the trajectory, and when we know it's going to move into the other quadrant, then we already tell the CPU to power up ahead of time.
Right, so basically one...
And then we just pass over the coordinate basically.
So essentially you'll have one core or some compute part running all the time to compute this one. And then...
No, it's really, it's not like a master core or something. It's really... This core here, for example, that's the only one run. Of course, there is at least one of the cores is running all the time, right? Because you need to track where the hand is. But it's not like there's a master core around that who's running the entire time, if that was the question. So it's really just this one core, and then it computes, okay, it's going to pass over. I'm going to activate that and pass on the coordinate. And now I'm going to activate that core and pass on the coordinate. So it's really just a handshaking nearest neighbor between the cores. There is no master scheduling core or anything around it.
For each core, like based on the events, would that restrict the amount of events you can detect?
If I do power shut-off, I mean, of course, the events coming from that quadrant are going to be lost, right? Because I just don't care about them because that's not where the hand is.
No, in the sense like you're shutting off one core and shutting on the other. So will that latency affect the events you can detect?
You mean the power up latency of the core? No, that's just what I explained. We compute a trajectory, and when it's likely to move into the next core, we power up the core ahead of time. So we have 0 latency in handshaking.
And will this, like you're continuously doing the switching on and switching off, so will this affect the reliability or?
No, not at all. Seriously not. I mean, we've had a lot of experience. We built multiprocessor systems on chip for mobile phones for like the last 20 years, all of them with DBFS, so we never had a reliability problem there. Right, so maybe because time is getting on, let's skip this one here. That one's quite interesting. So we did that with ex-Graz guys, Anand Subramani and David Kappel. That's our event-based gated recurrent units, eGRU. So now we're getting deep into the algorithms. So GRU is basically a watered-down version of an LSTM, right? So it's a recurrent network, but with simpler dynamics. But it's machine learning, right? You get real neurons, and you do the usual thing. You train it with surrogate gradients. The interesting thing is we can gate it, right? We can either gate it according to some amplitude in the local network, reaching some threshold, or in the later version, we even gate it according to confidence, right? That the subnetwork, the individual one or the individual eGRU unit reaches some level of confidence in its own decision and then passes that decision on. Basically, the idea is getting dynamic sparsity in here, right? So almost like a neuron, but at a higher level. But then we don't just pass on a spike because, yeah, we're in a digital world. I need to send a packet anyways. So sending a packet with a payload is not a much overhead. So we actually found not just the information of reaching the threshold, but also the internal state of the EGRU at that point is interesting and informative for the subsequent network. So then we pass on the entire vector of internal states, basically. Yeah, so yeah, that's just more of the equations. This is more of a shock and awe thing. But the interesting thing is, for example, this is actually, I think, DVS gesture recognition, but we also tried it on standard machine learning stuff. And we get on average for almost the same performance here compared to a very kind of data augmentation, LSTM, LXNet, so feed-forward, recurrent network, really state-of-the-art, very sophisticated network, almost the same performance at like 1/60th of the neuromorphic, of the numeric effort, right? So we really, it's not hand-waving. It's not comparing spiking neurons to ReLU neurons. This is really ReLU neurons to ReLU neurons. Lot less multiplier accumulates. So really a lot less memory access, a lot less computation, a lot less communication. So basically tuning all three knobs that way, right? And we even did a language model on top of that where we still got a factor 18 compared to implementing it, for example, on an A100. So that's one thing. Another thing we did was, again, I just mentioned it, state space models. So we figured out a way to make state space models kind of event-based in the sense that they can work directly with event-based data. So for example, stuff coming in from a DVS camera, but also point clouds, stuff like that. So you don't need to frame base it, or you don't need to introduce those exponential traces that other approaches do. So we are basically treating the individual events almost like a token going into a language model. In the form of an SSM. So we're really working off the exact times here, and we even do that in training. So that's the interesting part. So we can, again, efficiently train the state space model across something like 1 million spikes for each data point, right? So that's really taking very long kind of time dependencies into account. And there is this internal kind of exponentially kernel that's kind of circling around the real and imaginary that lets us pre-compute basically the nearest neighbor between, so there's always a nearest neighbor relation here, and that's the one we then enter into the model. So that's what we do in this model. So as I said, we can do that for point clouds as well, and there we, for example, treat then one of the coordinates as the time, or as a kind of linear axis, and the other two as the x and y. So something like that, yeah, it's kind of hinted here. Khalil, remind me, what does stream stand for? Khalil, a bit louder. Okay, so it was something with asynchronous, event-based asynchronous, whatever, recurrent network. Anyways, right, so we've got an input encoding, we've got the stream module. Published this on ICANNs. The interesting thing is this is the first network that actually has 100% performance on all 11 classes of the DVS 128 gesture recognition data set. So very first one that actually can do that. There is one thing from also this year that can do it on 10 out of the 11 classes, but not on this other non-gesture class, basically. So we really, the big thing why we're outperforming a lot of the others is really because we take the spike times, the exact ones, so we can be very precise, plus we can, because we're not frame basing it, we can do these long stretches of data, so we can work out a lot of intrinsic kind of interdependencies between the events. So yeah, for vision, for example, event-based vision, purely recurrent networks, no frames, no convolutions, and millions of events per sample, right? So we are way more complex databases, like, for example, DVS in automotive or something, because we basically only just touched the tip of the iceberg here. So we're really looking for way more complex data stuff here to really test what this model can do. Right, this is also an interesting one. So yeah, I'm jumping around a bit. This is really just teasers, so catch me afterwards if you want more details. Actually, for example, on the most of that stuff, Khalil also was a co-author. He's sitting in the audience here, so you can also catch him. So let's talk transformers. So it's, I think, going to be my last example. Or actually, no, I still have time. For some reason, my laptop, I started the laptop a lot earlier. That's where kind of the times disagree. Anyways, GPT, right? So your standard transformer network, if you just put a prompt to that network, you basically, that's the way it's trained, you activate at least 30–40% of all the synapses, all the neurons for even the most trivial prompt, right? Because information representation in a transformer network is just so spread out. So even for trivial tasks, I mean, this is just a toy example. You ask it, who's Luke Skywalker? And basically to generate an answer, you get a lot of active neurons, a lot of active synapses. Now, if you go to MT cortex, you actually get so-called Luke Skywalker neurons, right? So that's a neuron that only reacts to Mark Hamill as a picture, Luke Skywalker displayed as writing, or Luke Skywalker basically in audio spoken. So that's a very kind of more focused information representation that biology does. So that actually helps with sparsity, right? So if you have this very sparse information representation, there's a lot less and a more focused activation of the resources in network to answer a given prompt, right? Of course, this is kind of transmogrifying things, so this is, of course, not a large language model, but you get the point, right? To query information in the brain, it's much more focused. So that would be cool, right? If you have a prompt like, who's Luke Skywalker? And of course, yeah, ChatGPT tells you Luke Skywalker is a central character in Star Wars franchise, blah, 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 blah. How cool would it be for this prompt to only activate, yeah, a single neuron or only a very small subset of neurons in the large language model instead of, let's say, current ChatGPT, right? It's around 10 to the 12, 10 to the 13 synapses, or a large fraction of that. Sounds like science fiction? Actually doesn't. So there is the exponentially fast feed-forward networks from the ETH guys came out late 23, yes, because we just switch around. This came out in summer this year, Meta now in autumn this year, so they're all kind of going around there. So Google DeepMind calls it a mixture of a million experts. So they actually go in at the single neuron level and subselect, basically, even during training already, make this kind of way more focused representation that you basically have what I define kind of information highways, right? You activate a subset of the neurons in the token layer that really, in the MLPs, that only needs to be activated to answer this prompt. And the interesting thing is, when you do that, you notice that you get down to a tiny fraction of the resources in the network. So if you train this language model, for example, BERT model, in the right way, then for every given prompt, you only need 1/1000th. The interesting part, of course, is the algorithm that lets you search for that, right? Because if you have a very efficient kind of theoretical activation of your network, but if you need a huge search algorithm to figure out which neurons you need to actually activate to answer a given prompt, that of course kills your advantage. So what these guys, all of their own with slight differences, actually came up with was mostly these search algorithms, right? So the one from the ATH guys, that's actually log complexity. This one is square root complexity. So they're all still kind of searching for a very efficient search, but you probably can't go better than the log, actually. So log of the number of neurons in terms of what you need in complexity for the search algorithm. So that's actually, it's a shallow network, basically. It's a shallow network that searches for the neurons to activate, does it, again, very fast, and then to answer the prompt, you only ever activate those highways. And the interesting thing is, for example, the ETH guys, or also the Google DeepMind guys, they tried on TPUs, so tensor processing units, they tried on CPUs, GPUs, and only ever realized a tiny fraction of the theoretical advantage. And the ETH guys actually finished their paper with, we need neuromorphic hardware. Right? That's cool. So we're now implementing the ETH model on Spinnaker, and we also teamed up with Google DeepMind on their model, and just see how that fits on the machine, basically. So that's pretty cool stuff. It's mostly for inference, actually, at the moment. But of course, next thing, especially we're talking with the Google DeepMind guys, because they also have ambitions to do this for training. So really kind of also this very sparse kind of pre-training that you actually, if you have a given kind of data coming into the machine, you already know, I mean, not during the very early phase of training, but the later phase of training, you already know neurons that kind of specialize for certain types of data. So you only ever, with the back probe, need to touch those specific neurons, basically. So that would be pretty cool, because then you're actually also speeding up training. So that's one cool thing. And this is really kind of a convergence again, right? This is almost ideas from neuroscience needing neuromorphic hardware to be executed efficiently. There is not a GPU, not TensTorrent, not Samba Nova, not GraphCore that can actually support these kind of models at the moment. So that's pretty cool, and this is really machine learning having a problem, right? And figuring out an almost neuromorphic solution to it, right? We should have more of that. That's another example. So we're on concept 5 I'm going to show you. This is what we call block local learning. So what did we do here? So first off, we designed an autoencoder for fashion MNIST. So this is really taking the input space here, having a bit of a CNN network, having a bottleneck layer, and then blowing it up again, right? So that's what you call an autoencoder with a bottleneck layer. You're trying to squeeze down the relevant information about the input image as much as possible, and then see if you can blow it up again. And in this case, we didn't just blow up the original image again, try to kind of encode it and decode it, but we also tried to go for uncertainties so that the network tries to figure out where it's most uncertain about the reconstructed image, right? So you can see it here, for example. That's the original image with this writing here. That's the reconstructed one, and the network. So this is the error it does, and this is the predicted uncertainty. So the network is actually pretty good also, which is not obvious, at figuring out where it's uncertain about the reconstruction. Yes?
Previous slide, please. Can you go to the previous slide, please?
Yes?
So if we give a prompt which involves Skywalker and something together with it.
Yeah.
So I mean, you say that a single neuron stores all information.
No. That was me exaggerating, right? In the brain, there are these single neurons, but even they need to work in a sequence, right? They don't do this whole information storage just in a single neuron. It's more like pieces, right? So one neuron would maybe store this information. It's a central character in the Star Wars. Another neuron would store trilogy, whatever, protagonist, right? So you still need to activate. That's what I'm saying. You still need to activate for, let's say, again, you've got a 10 to the 12 model, for example. You still need to activate 10 to the 9 neurons to answer that prompt, right? But that's still only 1,000th, and you can actually still increase that probably. So I'm not talking about single neuron representation. I'm talking about still stitching basically a prompt together across these MLP layers, across the attention layers, but with a lot less of each attention layer being used in essence. Did that answer your question? Okay. Right, so to continue here, so we had this now autoencoder network with the bottleneck layer, and it can actually do a pretty decent job of predicting uncertainty. So where it knows that it doesn't know something, right? So what did we do? We folded the entire thing. So this is one part of the autoencoder network where we treat, so let's say this is YOLO, for example, or some other visual processing task. And you've got the class labels here. So we treat the class labels as the bottleneck layer. And the second half of that autoencoder network, where we blow up the network in a sense again, is just the mirrored image of that. And that's what we use for training, right? So we kind of, if you look at the last slide, this is the whole autoencoder. We kind of flip the autoencoder around like this. This gets the class labels. This is the input image. And the second part that's blowing up again is basically the feedback layers. Now, what does it give us? It's very interesting because we don't need like an ordinary backprop. You always need to hook up each class label all the way down to the individual synapse, right? You compute a gradient between exactly those two, which means a lot of overhead in communication, especially a lot of overhead in memory access. What do we do here? We only out here in the bottleneck layer, we only have the output losses. So this very reduced loss at the class labels. And then we feed the class labels into the feedback network. This feedback network at that point only needs fixed precision, right? It doesn't need floating point precision like regular, because we only ever kind of backpropagate across the same numerics as we did in this direction. So we don't need floating point, and we're basically blowing up the uncertainty, which is basically loss function, in stages and hierarchies. We're making higher and higher dimensional, but we don't have this initial high dimensionality that you do in ordinary backprop. So we have an unfolding, and we have an unfolding at reduced numerical precision. And only ever at the local subnetwork level, where we have basically local loss, that's where we really do backpropagation, standard backpropagation again. So that's interesting in the sense that, again, you can go, actually the output losses are sparse, so you get sparse, you get hierarchical, you get reduced precision, and you only ever need something like floating point precision at the very local level, right? So that actually helps you a lot in reducing the complexity of what you ordinarily get in backprop. And the interesting thing is, so there's lots of local learning rules around, right? Random feedback alignment, Geoffrey Hinton's forward-forward rule, all of those. But most of those break down if you go beyond MNIST, so if you go beyond 4 or 5 layers. We use this block local learning actually for large language models, for 70, 80 layer networks. So this is the first local learning rule that can actually do this very deep networks, right? Because before all the other networks, the gradient breaks down because you don't do this very kind of focused, targeted unfolding of the loss. It's more hazy what the others do. And that basically means you're losing the gradient, so really one to vanishing gradient problems if you go any deeper with the other local learning rules, right? So we get a lot deeper networks. As I said, only fixed point arithmetic, reduced communication, and we're slightly slower in convergence speed than backpropagation, but actually almost the same, and the same end loss basically, right? So we have a slight drawback, slightly slower, maybe 10, 20% slower than backprop in the training epochs, but the same ultimate performance of the network. So we don't, as I said, we get a lot of less overhead at a slight kind of speed disadvantage, but at the same performance. So that's pretty cool.
Christian?
Yeah.
What's the difference between the white layers and the grey layers in this image? You've got white blocks and grey blocks.
That is a good question. I'm actually not able, I need to look up the paper because it's been a while. That was like almost 2 years ago we did that. Now we're working on subset of that. I'm going to look it up and get back to you.
Yeah, just pop it on Slack, the paper.
Yeah. I popped the paper on Slack and I tried to answer it. And if you have really in-depth stuff, so this is David Kappel's work, then you contact him directly. There was some reason because it's also it's the direction of the local loss. Okay, I'll look it up. It was some way was the feedback and the other one was the computation of the local loss. Yeah.
And I wonder if the copies of each other knows.
Yeah. I get back to you. Right. So Spinnaker 2 in context. Yeah. So it's one of the first flagship projects of the German DARPA SPRINT-D. Yeah, and of course, together with Loihi, we represent the largest neuromorphic systems currently. We get evaluated by the US Department of Energy and by the German Environmental Protection Agency for kind of next generation data centers. So really energy efficient sustainability, right? You don't want to go the way that Microsoft goes and reactivate 3 Mile Island just to have an assistant in your world, right? It's not the way to go. Current commercial uptake via Spin Cloud Systems. I already said we've got a company there. So that's Sandia National Labs, Oak Ridge, Stanford. Actually, Deracia gets the system. Andreas has one around, right? Then Middle East, we actually smart cities are a big customer because they need to run like whatever 1,000, 10,000 robots at real time. And they, of course, do a lot locally in the robot, but they also need to have some data center that can handle this amount of data in real time. And there is not a lot of other solutions that have this built in, kind of at the cloud scale, this built in almost edge-like real-time performance. And of course, University of Manchester, right? And in Germany, Infineon, BMW, Schwarz IT, Potsdam. So we are getting pretty much around with all kinds of things. So from the single board level all the way up to multiple racks, basically. And of course, there's the machine in Dresden. You can access that remotely, or as I said, there's boards around at the workshop here. So that's the hard facts we have at the moment. So I didn't talk about drug discovery at all. I actually only talked about AI problems here, right? There's a lot of non-AI that we do in the machine. I hinted it. Drug discovery, optimization, symbolic stuff a little bit, quantum computing emulation. So Spinnaker is also good for a lot of only partially AI tasks where you need these other parts of the unconventional computing. Yeah, so we tried out a little bit on DNN training, as I hinted. Faster than CPUs, larger than GPUs, right? So 60 times faster optimization you actually compare to CPUs because the optimization algorithms on GPUs are not that good, right? So, and now we're working on these kind of mixture of experts models here. So again, let me go back to the very beginning. Right, so that's what I'm trying to put in, right? And I've given you examples. Like with the block local learning, we try to do things hierarchically, distributed. Also the eGRU is distributed, right? You've got subnetworks that run locally in each core, and only when they reach a decision do they actually transmit something, right? So that's also giving you temporal sparsity, right? If you have all these kind of gating layers in there, at the network level, and the individual, etc., at the attention level. I didn't talk a lot about asynchronity. Of course, the state space model I showed you, that's asynchronous, right? So that takes asynchronous data, but it actually also runs asynchronously based on that data. Recurrency is a big thing that I'm trying to put into Spinnaker. Why? Because recurrency kind of lets us do the same thing as biology does it, basically integrate information as it comes in, right? In ordinary feed-forward networks, I would need to synchronize a lot across the cores, do a lot of scheduling that basically, let's say I distribute one layer of a CNN network among multiple PEs, and I want to move that forward synchronously in time, then I need to do a lot of handshaking. It's better actually, again, if you do it with eGRU, for example, locally, or with the state space models, where the local state space model just runs in real time, gets sparse data from some downstream networks and just integrates it as it comes in, reaches a decision, and basically passes it on. So recurrency is actually a big tool for our machine learning networks to achieve this asynchronity, right? Because we can assume that the recurrent local network runs in real time, integrates information asynchronously as it comes in, and doesn't need to handshake like an ordinary feed-forward network, right? Reduced precision, I showed a little bit with the block local learning. Topology aware, I didn't show you a lot. We tried to put that in the eGRUs a bit. So basically the eGRU top level network is trying to be kind of locally dense, globally sparse. Also the block local learning is of course a little bit like that. This hierarchical learning, that's topology aware because you only ever at the top level, you need to pass on very sparse data, and only at the local level are you going really dense with the backprop feedback into the individual synapses, right? So that's how I try to put in these principles. Again, not necessarily doing everything with leaky integer and fire neurons. Coming from this application direction, I mostly start with a machine learning network and then stitch in kind of our bag of tricks here. Okay. Okay, so take-home message. This is actually from I'm doing a machine learning lecture at TU Dresden. I also have one lecture where I'm trying to tell them what could be bio-inspired about machine learning. So this is a slide directly from there. So if you look at biology, associative cortex, is that implemented in the machine learning stack at the moment? Partially in sensor fusion stuff. There is some stuff where people are trying to go neurosymbolic, but it's still largely missing actually. So people are very crazy on transformers, very crazy on deep neural networks. The integrating symbolic kind of on top of that, in the loop with that, is still missing. We actually also have some projects in that direction. We're integrating what's called NARS, non-axiomatic reasoning system on top of GPT, for example, and we can prove fact accuracy a factor 2 by basically running the symbolic I layer in a loop with the transformer, right? So advantage of the bias solution would, of course, be robustness and behavior outside the training space, right? Symbolic AI always kind of puts in a self-checking layer on top of stupid decisions that the DNN would make, right? Sparse encoding at all levels. You have, of course, some level of dynamic sparsity because you've got relu neurons, but that's not the have-all and be-all. So that's cool. It's mostly missing, but as I showed you, Google DeepMind, Meta, they're getting around to this way of thinking. And that, of course, gives you a lot of energy advantage. Also speed, right? Because you're not using your computational resources to do 0 times 0 calculations all the time. You're actually using them for where it makes sense, right? Structural plasticity, okay, didn't talk about that one, but we have some stuff where we do what's called deep R, deep rewiring, during the process, right? Pruning, what you do in machine learning, only works after you've got the network. We're doing this online, and we get actually high degrees of static sparsity at better performance of the resulting network. Yeah, and the rest, again, I said, recurrency, partial asynchronity, right? That's definitely, recurrency is catching up with the state space models at the moment, but still not all the way there. And definitely asynchronity is not at all there in machine learning these days, right? Okay, so that's the end of my talk, right? And the Spinnaker story continues, right? So, of course, there's Steve's group in Manchester, which is kind of winding down, but there's Davide and John, who are actually picking up the slack here, and they advertised a new professor there. So they're really trying to rebuild this group again. There's my group in Dresden. There is, of course, Spin Cloud Systems, who's commercializing this. And just to make a bit of an advertisement, Spin Cloud Systems is going to hire 40 to 50 new people this year. They got a hiring target from the investors to enlarge the company, go for multiple use cases. So feel free to drop in your CVs, right? They're always hiring. And there is, of course, Anand Subramani, who's just building up a group at Royal Holloway in London, with whom we do a lot of algorithm stuff, and David Kappel, who's recently moved to Bielefeld and also building up a group there. So a lot of collaborations on the algorithms with those two guys. And yes, another Monty Python reference, so please feel free to throw rocks at me now.